this series will be on polarization of light. So the question that we are going to solve in this video is based on Brewster's angle. So before proceeding, let us look at what Brewster's angle is. So we consider reflection at a given interface. So this is the interface. These are the refractive indices of the two media separated by the interface that we have. So we have an incident ray, and let us draw the normal to this incident ray. Then we will have a reflected ray, somewhat like this, as well as a refracted ray. So there will be refraction as well. Now, if we look at the polarization, so let us say our input ray is completely unpolarized. So we have unpolarized light as the input. So just for a clarification, a dot means polarization perpendicular to the plane. Perpendicular to the plane of incidence. And this symbol means polarization in the plane of incidence. Plane of incidence meaning plane of incidence and reflection. So over here, this dot means that the polarization is perpendicular to the plane, so it is coming out of the screen, so to say, coming out or going into the screen, that is the polarization. And this double arrow means polarization in the plane of the screen. So this is the notation. Now if this reflection is at Brewster's angle, that is if this angle is the Brewster's angle, then what we have in the reflected beam is completely polarized ray, which is perpendicular to the plane, and then the refracted ray will be partially polarized, like so. So this is our incident ray. Incident ray is unpolarized. Let me write it again properly. Incident ray is unpolarized. Why unpolarized? Because it is having polarization both perpendicular to the plane and parallel to the plane. Reflected ray, this is the reflected ray. This is polarized. This is perfectly polarized, completely polarized, and polarization is perpendicular to the plane. And this is the refracted ray, and this is partially polarized. So this is a feature of Brewster's angle, that if the ray is incident at an interface separating two media at a certain angle known as the Brewster's angle, then the reflected ray is going to be completely polarized, with polarization being perpendicular to the plane of incidence. Now the formula for Brewster's angle is, let me write down. This is the formula for Brewster's angle. So tan of the Brewster's angle is the ratio of the refractive indices of the media separated by the interface. Another important feature is that if we consider this angle of refraction to be, let's say, R, then we have another relation which says, so this is another relation. That means that this R plus theta B is 90, and since incident angle is same as reflected angle, so this angle is theta B. So this plus this is 90, which means this is also 90. So these are the two relations. These can be found out from Fresnel's reflection coefficients and the Snell's law. We would not be looking at the proof in this video. We will be using these two relations to solve the problem. So let us now look at the question that we have to solve. So question. The question says, light strikes a water surface at the Brewster angle. Brewster angle is also known as the polarizing angle because the reflected ray is polarized. So at the Brewster angle, the part of the beam refracted into water strikes a submerged glass slab and the refractive index of the glass slab is 1.5. We will draw the diagram later. Let us write the question first. The light beam reflected from the upper surface of the slab is completely polarized. Find the angle between the glass slab and water surface. So let us first draw the diagram corresponding to this question. So we have an interface. This is air and this is water. We have incident ray at the Brewster angle. So there will be a reflected ray and then there is a refracted ray. This refracted ray is then incident on a glass slab. So this is the glass slab. And then we are told, let us first draw the normal to the glass slab. We are told that this reflected ray from the glass slab, from the upper surface of the glass slab, is completely polarized. So this ray is polarized, and then there will be some refraction into the glass medium, and then the ray will come out parallelly to the incident ray. This is the refracted inside the glass, and this comes out. So this is our diagram. In this, we are supposed to find out the following angle. Let me show which angle we want to find out. So we want to find out this angle, this theta. This is the angle between the glass slab and the interface of air and water. So we are supposed to find out this angle theta right here. So let us look at the question and solve it. Let us call this theta B1, and since we are told that this reflected ray from the glass slab is also polarized, and we know that reflected ray will be polarized only when the incident ray is at the Brewster angle. So this angle is also a Brewster angle. This is theta B2. This is Brewster angle corresponding to the water glass interface. So this is glass. This theta B1 is Brewster angle corresponding to air water interface, and theta B2 is Brewster angle corresponding to water glass interface. So let us use this relation right here. Tan theta B is N2 by N1. So we have tan theta B1 is equal to refractive index of water over refractive index of air. Refractive index of water is roughly taken to be 1.33 and air is roughly taken to be 1. So plugging this into the calculator gives us theta B1 is approximately 53.06 degrees. This is Brewster angle for the air water interface. Next, let us find out the Brewster angle for the water glass interface. So we have tan theta B2 is equal to refractive index of glass over refractive index of water. So this is 1.5 over 1.33. This is roughly 1.13. So this gives us theta B2 is approximately 48.44 degrees. Now let us do some geometric construction to find out theta in terms of the angles that we have. So if we extend this normal, all the way, so this angle, we know this is a normal to the surface, so this is 90 degrees. And let us call this angle as the angle of refraction from the air water interface. Let us call this R. So since this is also a normal, this angle right here is going to be 90 degrees minus R. And since sum of angles of a triangle is 180 degrees, so this angle is going to be 180 degrees minus 90 degrees minus R. Let me rewrite this water somewhere here so that I have some space. So minus this angle minus theta b2. So this is this angle. This we found out because sum of these three angles needs to be 180 degrees. This angle we know, this is a triangle. We are looking at this triangle, this point, and this point right here. So this is theta b2. This is 90 degrees minus R. So this will be 180 degrees minus 90 minus R minus theta b2. So we can find out this theta now by considering this point, and this point as the triangle. And this angle is already 90 degrees. So sum of this theta and sum of this angle needs to be 90 degrees. So let me first simplify this angle. This is 90 degrees plus R minus theta b2. So from this triangle right here, we know that theta plus 90 degrees plus R minus theta b2 should be equal to 90 degrees, because sum of angles in the triangle needs to be 180 degrees and this angle is already 90 degrees because it's a normal. This line is a normal, so this is already 90, so sum of these two should be 90. So theta plus 90 plus R minus theta b2 should be equal to 90 degrees. So this gives us theta is equal to theta b2 minus R. So we have found out theta b2 and we need to find out now R. So to find out R, we will use Snell's law. So Snell's law. So Snell's law says that if we have an interface and we have an incident ray at some angle of incidence, say theta I, then we will have the reflected ray at the same angle, but for the refracted ray, let us call this theta R. So and this is N1, this is N2, and this interface is there. So according to Snell's law, we have N1 sine theta I equal to N2 sine theta R. So this is the Snell's law. Let us use this for the air-water interface that we have. So in our example, we will have since the incident angle is theta b1, or let me write it here. So we have incident angle for the air-water interface is theta b1 and refracted angle is R. So we have this. This means refractive index of air is taken to be 1, for water is taken to be 1.33. So theta b1 we found out is roughly 53.06 degrees. So plugging this value in the calculator, so this is 1 over 1.33 sine of 53.06 degrees. This comes out to be approximately 0.6. So this gives us, again plugging into the calculator, roughly 36.87 degrees. So now we have all the angles needed to find out our theta. So let us do that. Theta is equal to theta b2 minus r. So theta b2 is approximately 48.44 degrees, and r we just found out is roughly 36.87 degrees. So this gives us 11.57 degrees. So this solves the problem. This is the angle that the glass slab or the top surface of the glass slab makes with the air-water interface. This is the angle that we were supposed to find. Find the angle between the glass slab and the water surface. So this theta we have found out to be 11.57 degrees roughly. So the takeaways from this question were the Brewster's angle, this expression for Brewster's angle, and the polarization by Brewster's angle, and using Snell's law.